Good afternoon, Internet. I am Matt Booyak, and in this video we'll be taking a look at the 46th problem from the Project Euler Problem Archive. Now, before we dive into the details of this problem, I want to talk about the problem that I did not solve yesterday, problem number 44. Now, I was scheduled to solve this problem yesterday, but I was having a little bit of difficulty coming up with a solution that was both efficient and easy to understand. My first attempt at a solution turned out to be much slower than I expected, and though I had an idea for a more efficient algorithm, I didn't have a chance to completely work that out before it was time to record. And so instead I moved on to problem number 45 with the intention of coming back to this problem. Now, since yesterday, two things have happened. One is that I tested out my improved algorithm, and it does in fact perform beautifully. But it does require a little bit more preparatory analysis, and so I expect the video will be a little bit longer. And so that probably won't come out until maybe Friday of this week. The other thing that happened is I received an excellent suggestion from a viewer of yesterday's video who had an idea for how to efficiently determine whether a number is pentagonal or not. Just by chance, both problems 44 and 45 deal with pentagonal numbers. And so I tried applying Jacob's suggestion to my original approach to problem 44, and it speeds it up just enough that I consider the result to be passable. It still takes about 30 seconds to come up with the answer. Keep in mind that may sound just fine, but this problem is 20 years old. 20 years ago, computers were 1,000 times slower. It's easy to forget. But that means that 30 seconds today would be much, much longer 20 years ago. In any case, I decided I'm going to also make a video going over my original approach, explaining why your intuition, or certainly why my intuition, was not quite right with respect to the efficiency of that algorithm, and also show you Jacob's approach to determining if a number is pentagonal. So that will also be coming in a video later this week. For now, let's get back to problem number 46. So this problem asks a question about a conjecture by Christian Goldbach. It's referred to as Goldbach's other conjecture because the famous Goldbach conjecture deals with the sums of prime numbers. This is a different conjecture which states that every odd composite number can be written as the sum of a prime and twice a square number. Turns out this conjecture was not true. And so we are tasked with finding the first number which violates this conjecture. Our approach will be pretty straightforward. We're going to take each odd composite number. We're going to consider all of these square numbers that are less than half of that number, and we're going to try subtracting them from our original odd composite. And if any of them result in a prime, then that number does not violate the conjecture, and we would need to keep searching. And we'll continue searching until we find the first number that does violate the conjecture. So with all that in mind, let's get into it. As usual, we will copy our problem directory, or excuse me, our template directory to make our problem directory. Enter our problem directory and open our main.cpp. Now, in order to solve this problem, we will need to be able to determine if a number is prime or not. Unfortunately, I did a whole series on prime numbers, determining if they are prime, generating prime numbers. I'll put a link to those videos in the description. But for now, we just need to do include primes.h. And also go to our make file and link in LNum theory, which is our number theory library. Okay, so now we are ready to do work with primes. So as I mentioned, we're going to loop over all the odd composites, and so we'll say we'll say n is equal to 9. That's the first odd composite number. We won't have a termination condition. We're just going to keep going until we find our answer. And at each step, we're going to increment by 2, not just by 1, because we're only interested in odd composites. Next, we need to determine whether our number actually is composite. And so now we'll need to create an instance of that primes class that I mentioned. So we'll say primes p. And we'll say if not p dot is prime, excuse me, if it needs to be composite. So if it is prime, then we will go on with the next candidate. Next, we want to consider odd numbers, or excuse me, square numbers that are less than half of n. And so we'll say for int m is equal to 1, 2 times m is less than n, increment m. And we'll need a way to keep track of whether we have found a value of m which leads to a prime number, because if we do find such a number, that means that n does not violate the conjecture. So we'll say bool solution equals true. That is, we're setting it, initializing it to true, and if we find any number which satisfies the conjecture, then we will set solution to false, indicating that we have not yet found a violation. So we'll say if p dot is prime n minus 2 times m, we'll say solution equals false. That is, the conjecture has been satisfied, and so this is not a violation. Then we'll break, and if we've tested all of the values of m and none of them leave a prime, that means we have found our violation and solution will be true. So we'll say if solution printf solution is equal to n, and then we're just going to return 0 straight from main, which means we will never actually reach this line. We can delete that. Okay, should be good. Let's go back to our shell and make and run. And it says our solution is 5777. Let's check that out. If we go to the archive, go down to problem 46. As is often the case, I have been signed out. So please give me just one moment. Now we're signed back in, and we can check that 5777 is indeed the correct answer. So as always, thank you for joining me in this video. Tomorrow I expect I'll tackle problem number 47. But these days, who knows?